Hello, hi everyone. This is Tushar from Rasayanika, expert for chemical sciences. So today I'm here to help you understand Michaelis Menten equation and Lineweaver Burk plot. Now these two are very important concepts in the topic of chemical kinetics for CSIR net. So before we move into Michaelis Menten equation in detail, let's understand what is an enzyme and what is a catalyst, because these two are the topics that we will be dealing in Michaelis Menten equation. Now, what is an enzyme? So enzyme is a substance that acts as a catalyst in a biological system. So they change the rate of reaction in a biological system. They either increase the rate of reaction or decrease the rate of reaction. Now, what is a catalyst? So catalyst is defined as any substance which increases the rate of reaction without being consumed in the reaction. It is important that it is not consumed in the reaction and it is recovered. It can be recovered once the reaction is complete. So a catalyst is a substance which increases the rate of reaction without being consumed in a reaction. Now let's move to some characteristics of catalytic reactions. Now, as I've said earlier, that catalyst increases the rate of reaction. Now, why does it do so? It does so by decreasing the activation energy. This is the first point, that catalytic reactions proceed through a reduced activation energy. You can see here the reactant is given here and the product. Without the catalyst, the activation energy is higher. Now, with the help of catalyst, the activation energy has decreased. And as you know from kinetics, when the activation energy decreases, the rate of reaction increases. Now, coming to the second point, due to the use of catalyst, the equilibrium constant does not changes. Once again, why? Because the catalyst will increase the forward reaction in the same manner as it does with the backward reaction. So the position of the equilibrium does not changes. It just happens that the equilibrium is attained quickly, but the position or the equilibrium constant does not changes. Now, these catalysts are very specific in their function. Suppose, let's say a catalyst is catalyzing a reaction for A to B. So it will only catalyze for this set of reaction. It cannot catalyze for B to C. So these are very specific in nature and they are very potent in nature. That is, a very small amount of this catalyst can also give a higher productivity. Okay. Now, coming to the last point, the catalyst does not alter the nature of the product. That is, it only increases its rate of production, only increases the rate of production in a very short time. So we can only increase the rate of production, but we cannot alter the nature of the product. Now, coming to the Michaelis and Menten proposed a two-step mechanism for this reaction. Step 1 involves the formation of the enzyme substrate complex, which is ES complex. Here, enzyme coordinates with substrate to form the enzyme substrate complex. And in the second step, this enzyme substrate complex is decomposed to give the product. Now, the important thing to note that the first step is the equilibrium state or the fast step. And the second step is the slow step. This is the slow step. So as we know from basic kinetics, that the slow step is always the rate determining step. So the second step is a rate determining step. Now, how can we find the rate of this reaction? We can find this using the second equation, where the rate of formation of product dP by dt is equal to, here you can see the rate constant K2 and the enzyme substrate complex concentration. Now this ES, this is the enzyme substrate concentration. This is an intermediate. So as soon as it is produced in a reaction, it will be consumed. So eventually it is constant. Its concentration is constant in this reaction. Hence, we can use steady state approximation and solving the equation by using and changing various parameters, we will get Michaelis Menten equation. Now this equation, where it is R is the rate of the reaction, where K2 is the rate of formation of rate constant of formation of the product, E0 is the initial concentration, E0 is the initial concentration of enzyme, where S is the substrate concentration. And this parameter Km is Michaelis Menten constant. So the Km is given by the rate of decomposition of the ES complex, which is K1 inverse, as you can see here, it is K1 inverse, and K2 divided by the rate of production of this ES complex. Now, what is this importance of Km? So Km shows the affinity. It shows the affinity. The physical significance of Km is it shows the affinity of the enzyme to the substrate. The lesser the value of Km, the more it has the affinity towards the enzyme. The enzyme has more affinity towards the substrate. Okay. Now, when the rate of the reaction will be maximum, the rate of the reaction will be maximum when all the enzymes, this is the initial concentration of the enzyme, all the enzymes is converted into the enzyme substrate constant. So the Rmax, what we have got? We have got rate is equal to K2 into the concentration of enzyme substrate complex. So since we have all enzyme substrate complex as the initial concentration of the enzyme, so our Rmax will be K2 into initial concentration of enzyme. So this is the maximum rate we can achieve. Now substituting this in previous equation 2, we will get the final equation which has a relation between the rate of the reaction and the maximum rate that we can achieve into the concentration of the substrate divided by Michaelis Menten constant and the substrate concentration. Okay. Now using this, we have three cases. So till now what we have got? We have got rate which is equal to the maximum rate that we can achieve into substrate concentration divided by Michaelis Menten constant plus substrate concentration. Now we can have three conditions. Suppose the first condition is when we have Km much greater than substrate concentration. So if it is the case, then we can neglect the substrate concentration of substrate can be neglected. Hence our equation will become this: the rate will be first order with respect to the concentration of the substrate. Okay. Now coming to the second case where the substrate concentration is very much in comparison to Michaelis Menten constant, what will happen? So it will show this: the Km will be negligible. So if the Km will be negligible, so eventually we are left with the maximum velocity that, or the maximum rate that we can achieve. Since Km is negligible, we can neglect that. So we are left with this. So this will cancel out. So the equation becomes the rate will be Rmax. So this will be zero order. This will be zero order. This will be zero order with respect to the concentration of the substrate. This will be first order. Now let's see the condition where the substrate concentration is equal to the Km. So the substrate concentration, when the substrate concentration is equal to the Km and we substitute these values, we'll get R is equal to the maximum rate that we can achieve divided by 2. So here the important point to note here is mathematically the Km is the concentration of substrate for which the maximum velocity or the maximum rate of the reaction is half. Okay. Now using this parameter, we can draw this plot where rate of the reaction is taken in the y-axis and concentration is taken in the x-axis. Now as I have said, when this is the case when the concentration of substrate is maximum, so it is zero order, you can see that it is completely linear. As you can see, this is reaching the maximum rate of the reaction. So this is zero order. The more we change the concentration, it does not affect the rate of the reaction. Now coming to the point, to the initial point, here you can see the rate of the reaction is first order. As I have already said, when the substrate concentration is less, the reaction is first order. So since it is first order, we have this equation, and I have mentioned earlier that when the substrate concentration is equal to Km, the rate that we get is exactly the half of the maximum attainable rate that we can achieve. Now, what is turnover frequency? Now, turnover frequency can be defined as the number of catalytic cycles performed by the active site in a time interval divided by the duration of time interval. So we can say it in other words, number of molecules of reactant that are converted into product by a single active site in a unit time. So this is given by Kcat. This is equal to K2. K2 is the rate constant for the formation of product. So this K2 from previous equations, we know K2 is the maximum velocity, the maximum rate of the reaction that we can achieve divided by the initial concentration of the enzyme. Now moving to the catalytic efficiency, epsilon, it is given by the ratio of Kcat, which is the turnover frequency divided by Michaelis Menten equation. Now if you can note this, this is the resultant rate constant for the rate when we have very less concentration. So when we have very less concentration of this, we are left with Kcat by Km, concentration of E naught into S. As you can see from this one, when we have very less this. So here in this point, so this is the effective rate constant. Since this is the effective rate constant at the lowest point, so the catalytic efficiency talks about the kinetics of the enzyme at very low concentration of the substrate. This means how well an enzyme is performing even at the concentration where the substrate is very less. Now, from the Michaelis Menten equation, we can derive this equation for the Lineweaver plot, where this plot is between 1 by R, here it is 1 by R in the y-axis against 1 by substrate concentration. If we plot this, so this is our slope and this is our y-intercept. So y-intercept is given by 1 by the maximum rate, whereas the x-intercept is given by negative 1 by the Michaelis constant. So x-intercept is given by negative 1 by Km. Okay, so the slope for this Lineweaver Burk plot is Km by R max, and the x-intercept is negative Km. So that's all about the Lineweaver plot. So in this session, we have discussed in short what is Michaelis Menten equation, various parameters that includes, and the plot for Lineweaver Burk plot, which is a plot between 1 by R. This is inverse of the rate constant versus inverse of the substrate. Thank you. Please do like, subscribe to the Rasayanika channel for more such contents and videos. Thank you all to be with me.